And most all of you are going to remember, probably with a little bit of fondness, the conversation about kinematics from the beginning of last year. Mostly because kinematics is very accessible to students. It's relatively straightforward. Most students do pretty successful with it. But in general, the thing that most students like about kinematics is that once they've kind of got it nailed, it's not too terrible. The problem is that what I taught you last year in kinematics is a far cry from what you need to know this year. But at the same time, kinematics isn't physics. So I want to start from the beginning understanding that. Kinematics is what you have to teach students so that they have a common framework and vocabulary. But it's not really physics. It's a consequence of mathematics. But it's not really physics. So let's understand that from the beginning. Physics is an attempt to explain why things happen the way they do. Kinematics just tells you what happens. You provide the parameters, it tells you what happens. Kinematics is the study of motion. Thus, kina, the root word, kinetics, kinetic energy, study of motion. Matics, of course, you know from other words, is study of. So kinematics is the study of motion. And let's stop at this instant and take a survey of what it is you guys might remember from kinematics from last year, those of you who have a last year upon which to draw. Now, be careful here. I'm not easily fooled. All of you had to make it through physical science. So just saying that you didn't have physics last year doesn't absolve you of having to have known things from physical science. You remember physical science. That's right, half chemistry, half physics back in the 8th grade. Yeah, almost all of you had to have it. I don't think there's a person here who didn't suffer through middle school. Yeah, well, some of you liked middle school. And you all should suffer a terrible, horrible fate. There's no reason to like middle school. And I'm really hoping my wife is listening right now. She's not, but she should be, because middle schoolers are terrible things, aren't they? Anybody here have any relatives that are still middle schoolers, little brothers and sisters? They're terrible things, aren't they? The thing I tell my wife about middle school all the time is that once you start teaching middle school, you need to have a separate set of clothes that's just for middle school, because you never get the smell out of your clothes if you start teaching middle school. She doesn't like that joke very much because it's true. That's the whole truth of the matter. Middle school. Anyways, what I'm writing down here, of course, is something that many of you recognize right away. So let's see. You guys see my picture, right? Any trouble identifying my picture? Oh, good. So here's what we're going to do today. I'm going to send you off to talk with some friends in some breakout rooms. And for those of you who've never used a breakout room, well, yay, this is your first time. And in a few minutes, I'm going to pull you all back together, and I'm going to start seeing what you guys remember from this, okay? What I want is the answer to this question, and this question's pretty simple. How many different things could you tell me from this picture I've just presented you? Everybody understand what I'm asking? We'll see. Physics or no physics, you all are supposed to be able to read a graph. So, all right, so I'm just going to kind of pick people out at random, playing a little bit of a participant shuffle. And the first one is, James, can you give me one thing that we can figure out from this graph?
You can figure out the acceleration of the object.
All right, so if I was to ask you how to figure out the acceleration, could you tell me?
It'd be the slope of the graph.
Thank you. Fantastic. And we'll play roulette again, and I get, let's see, Kelly Wells, give me something else I can figure out from here.
You can get distance traveled.
Okay, I can get distance traveled?
You take the area of the triangles and find the distance.
All right. So let's see. Since we're talking about area of the triangles, somebody else tell me another distinction that could be made with the area. And I'll allow a volunteer for that one. Go ahead, Joey.
If you take the absolute value of the areas, then that would be the distance traveled. But then if you're just taking into account the direction or the sign of whether it's above or below the axis, then it's displacement.
All right, so absolute value of area gives you the distance, but if you just take the areas and include their sign, you get displacement. Thank you. Now let's keep going with this roulette thing. I got Lauren. Do you know anything you can tell me about this?
Yes. We know that the initial velocity is 40 meters per second.
All right, so picked off some pieces off the graph. We're starting to run out of things here. What's that?
Another thing is that we assumed that the final velocity was negative 40 meters per second.
All right, so you can probably get the initial and the final velocity. Fantastic. And I think there's still a few more things we can get here. So let's see, Brett, do you have any ideas of what else we can get here?
I didn't see what time it was, but at one point in time, it was at 5 meters per second.
Potentially, I'm sure that it might.
I saw like a little symbol where it said 5 meters per second. I just don't know when it was.
I'm gonna say that maybe I'm sure that that's true, but it's not very clear from the graph. We might be able to figure that out. But there are some things that the graph tells us that are fairly clear on the onset. John, can you give me another piece of information?
I guess you could say that did someone say the initial velocity is 40 meters per second?
Somebody did say that, yes.
It goes along 10 seconds, I guess.
All right, that we have an idea of what the time interval upon which we were observing this object, and it appears to be 10 seconds. So, yeah, we get that right here. So the length of time of the observation looks to be about 10 seconds. There's a few things missing, so is there anybody else who wants to offer something that might not have already been said?
Did we already talk about the acceleration
Yes.
and the velocity
Yes.
and the speed?
No one said the word speed, but if I was to show you the list I've been keeping, this is the list I've been keeping. We've got acceleration, which is slope of the graph, distance and displacement, which deal with the area, slightly different, initial final velocity, information about the time interval, and probably potentially the idea that we could figure out other velocities that the object might have attained during the interval. Of course, this is a velocity versus time graph, so the truth is we can pick any point along this line, and I should be able to tell you what the velocity was at that instant in time. That would be the instantaneous velocity. The velocity at a single moment in time. Now, all of these are vocabulary words for students who have had physics before. Now, for students who are just joining us with physics for the first time, these might sound like new pieces of information. And there are some things I want to make sure that we kind of drive home, but is there anything else that could be deduced from this graph?
The average velocity and average speed?
Sure, we could find average velocity and average speed. Those are other pieces of information that we could get from the graph. They're a little bit more complicated because those are reliant upon knowing the definition of average velocity and average speed. And those definitions are specific and don't allow for us to have much flexibility. There's two big banner things that are missing here. The first is the one I would hope to have gotten from you before we started any of this, which is you should be able to provide a written or verbal description of what this object might have been doing. Before we even launch into the specifics that can be obtained from the graph, graphs are visual representations of something that was observable in nature. And I want to be very clear, it doesn't matter what the graph is about. For all of us here in any science class, a graph is supposed to be the visual model. Go ahead, Alex. You got your hand up?
I can try to explain the graph if you want me to.
I would love to hear what you think is happening.
So the ball starts by rolling up like a ramp or something, and at the top, at 5 seconds, its velocity is 0, and then it rolls back down the same distance.
All right, so I think Alex probably gave us a great representation of what this object is doing. We have a clear indication, And at this moment, let me just kind of downshift for a moment and break the fourth wall and say to all of you who have never had physics before, I'm going to go over what I feel is what you should be able to do with any graph to which you are presented and what my expectations would be. And for the rest of you, understand that it is quite plausible you will be presented with a graph which you may never have seen before. And my expectation this year, just like last, is you should be able to provide a picture of what you might be observing from the graph. So let's start by understanding something, that a graph is a representation of something that might have been observed. But don't assume that a graph is always observing some moment in time. The horizontal axis tends to be the axis that gives you the kind of segment upon which you're observing. This graph is clearly observing a moment in time, approximately 10 seconds, maybe more. But the horizontal axis could have been position. I want you to think, if you had a graph that graphs something versus position, you could have elevation versus position. That'd be a topography map. There are lots of ways where graphs can compare something else along the horizontal axis. We tend to believe that the horizontal axis and the vertical axis are fixed, but they can be particularly flexible. For us, as physics students, we see time on the horizontal axis a lot, but please don't become complacent about that. If I really wanted to screw you over, I would put something else there just to see if you can roll with the punches. But a graph is supposed to tell you something. This graph is telling us what the velocity is for every moment in time over the period of 10 seconds. Now, generally, before students should go and launch into what's happening with the graph, I would assume they didn't know what the graph was presenting them and that they would have to spend some time evaluating it. What I mean by that is you should always, whenever faced with the graph, consider the possibility that the slope of the graph and the area under the graph might have some kind of value. You may not know what that value is straight ahead. You might need to kind of consider it. A trick to consider what those might be is to take a look at the units that are being presented to you with each of the axes. For example, time is being presented in seconds. I know that because I see an S next to the units that are here. That clearly suggests seconds. And the velocity is being presented in meters per second. So if I wanted to see if the slope had any meaning, the first thing I would do is find the quotient of the vertical axis to the horizontal axis by just observing the units. In this case, that'd be meters per second over seconds. And see if the result of that represents a unit that I recognize. In this case, it's one I do recognize. I recognize it as acceleration. But you could just as easily be graphing energy versus position, which would give you a slope of joules per meter. That doesn't have a whole lot of meaning. So not always will the slope have meaning. But when it does, you should consider that the slope might be trying to tell you something. Area is another place you should visit. To consider what the area might be, you do the same thing, but this time you're looking at the product, not the quotient. So I'm going to take meters per second and multiply by seconds, which gives me meters. Meter suggests position, displacement, distance, length. Any one of those could be the result of finding the area. It's not obvious, however, it's something to test. The units can often lead you to what you might be able to ascertain by looking at the slope and the area presented. Now, that being said, this graph specifically can't tell you some things. But clearly, from looking at these pieces of information we've developed, this graph can tell you quite a bit. It can tell you the initial velocity, the velocity at the beginning of the interval. Why? Because I have a time equals 0 point. That's when we started observing the object. That's why that's true. Does it tell us the final velocity? That's a little bit more ambiguous, and I want to be careful about this. It tells me the velocity at 10 seconds, But should the object have continued to move, there may have been other factors affecting the object to which we are not privy, because our graph stops at 10 seconds. So it tells me the final velocity over a period of 10 seconds. It doesn't necessarily tell me anything more than that. And I know you guys are wondering why I'm being so specific, because they're going to ask questions that might lead you to believe you might know more than you don't, or that you might know more than you actually do from what's been given. Distance and displacement, both clear. Yep, you can get those right from this graph. And the only thing I want to make sure that you guys who are fresh to this know is there is a difference between calculating distance and calculating displacement. Distance is finding the area under the curve, but taking the absolute value of each area. So I have to break up my areas by section. Sections that might have positive values and sections that might have negative values. On the other hand, the displacement is the absolute change in position, therefore it is the areas without taking the absolute value. Now, students make mistakes here all the time. Make sure you understand. Taking the area means looking at the part of the graph that binds the axes to the curve. And although this is a straight line, it's always referred to as the curve, even if it's not curved. This graph can't tell you position. This is important. Know your limitations. So this graph never tells us where the object is. It merely tells us how the object's position has changed. Now, there are other factors here and other features here that I do want to call up, and I want to make sure you guys are seeing them, at least as clearly as I'm seeing them. So let me kind of clear this out for a minute and get rid of some of this distraction. There we go, nice and clean, ready to start again. And I do want to put in my scale. So there's my scale. It's important to note that this graph is a straight line for two reasons. One, just pragmatism. You can find the slope of any straight line. You have the mathematical, technical skills to do so. So giving you a straight line means I'm giving you something to which I believe you have the technical skills to utilize. More importantly, there's no reason to believe that you have the skills to recognize the difference between a parabola and a value like t to the fourth. Meaning a parabola and something that is to the fourth power would have similar curvature. A curved graph may present you with information that is misleading. You can't assume quadratic unless you prove it. You can't assume something to the third unless you prove it. Straight lines are the only thing you can count on. It's important to you to understand that. If you're given a straight line, you're being told specifically that one of the values changes in a regular and measured way. And they are expecting you then to have some kind of mathematical skill to understand the way in which that object varies. But if they give you a curve, then you're probably being told that the object varies in a way that might be unpredictable. You may need extra information in order to tell what kind of change is taking place. However, there are tricky questions here. At 5 seconds, is the object accelerating? I'm looking to see what those heads do, because that's an important question. It's one of those questions that we know is going to be thrown on tests just to see if you're paying attention. And for everybody here who understands that acceleration is the slope, there's the understanding that if the acceleration is the slope, as long as the object has a non-zero slope, it's accelerating. So, James, you have a question? You're muted, so.
I was just going to answer that because it's like saying, is it accelerating?
Right. So, well, what were you going to say? I'd love to hear
I
it.
was going to say yes. It's continuous acceleration.
Right. This is a continuously accelerating object. There is a prevailing idea out there that objects that are stopped don't accelerate. And although we might not have a firm grasp on what acceleration means, understanding that acceleration is change in velocity should tell you that anytime an object's velocity is changing, it's accelerating. Something changed this object's velocity from moving to stopped. That meant it accelerated in order to stop. But it doesn't stay stopped forever. Something changed its velocity from stopped to moving. So it was accelerating the whole time. That's clear from the graph. The only way an object would demonstrate a lack of acceleration is if the object had a zero slope somewhere along the velocity versus time graph. All right. Motion equations are not difficult to understand, and kinematics isn't either. But this isn't physics. Physics can give us, from looking at a system, a result that might be a motion equation. But what a motion equation does is merely tell us where the object is at some future point in time. It doesn't tell us why the object does any of the things it does. It doesn't really give us an ability to control the object. It doesn't give us any ability to kind of understand the bigger picture. It just tells us what's happening. And you guys kind of nailed it. The object was probably rolled up a hill. It rolled up the hill, stopped, and rolled back. I know that it had a positive velocity at time zero. That velocity got smaller and smaller and smaller and smaller until it stopped. And then the velocity became negative. Now, I have to make a lot of assumptions here. For example, I'm assuming it's moving in one dimension. That's a pretty good assumption, but I am having to assume that because I have no other data to the contrary. So there are many assumptions being made here over the top of this larger picture, but I wanted to use this as our start of review. So with that, next year, when I come back to this picture, my expectation for all of you, but definitely the folks who have been in physics before, is that when you look at this picture, and I'm trying to get rid of the distractions for just a minute. When you look at this picture, instead of seeing it as specific numbers, see it symbolically. This is the initial velocity. This point represents some future time interval. This point represents that final velocity. The slope of this line is the acceleration. Considering what I see here, if I wished to calculate the slope, I would look at the change in the horizontal, the change in the vertical divided by the change in the horizontal. Isn't that how you guys calculate slope? The change in the vertical would be v minus v naught. Take the final number minus the initial number and subtract them. The change in the horizontal, t minus 0, because 0 is my origin. A little bit of mathematics and I would get v equals at plus v naught. One of Galileo's motion equations. Now, I could do the same thing in talking about displacement. Displacement's a little bit harder though, because is there a way to find this area? Is there a function that does so? A lot of people would say that, no, they'd break it up into two different triangles, but I would like to do it as one triangle, or at least one shape. Most people don't know this, but you guys who had me last year should, that this is a trapezoid. It's what would happen if you took a trapezoid and treated it like a sunshade. Folded it. It's still a trapezoid though. And a trapezoid's area, which we said is displacement, is 1/2 times the sum of the bases times the height. Well, for this trapezoid, time is the perpendicular, so it's the height. And the sum of the bases would be the velocities. Now, in an AP Physics 1 class, we would develop this over a couple of days, but I don't want to do that because this is another potential motion equation. Now, you guys who are new to physics, please notice there were 5 motion variables. Each of these motion equations appears to have 4 motion variables within them, suggesting that they are useful only in specific circumstances. A circumstance in which you have 3 of the 4 motion variables and you're searching for that 4th one. I'm saying that because this particular relationship is useless if what you need is displacement. It doesn't appear in the relationship. And this one is useless if you need acceleration because it doesn't appear in the relationship. But because you have 2 relationships that together have all 5 motion variables, you should be able to solve any problem. However, let me speak directly to the folks who are new to this for just a few moments. We consider that there might be 5 specific motion variables. And let's see if you guys can name them all. Just start shouting them out. Unmute yourselves and start giving me variables.
Acceleration.
Acceleration will be represented as a lowercase a in this class, generally. Angular acceleration will come up later where we'll dive into the Greek alphabet. But for now, lowercase a. Go ahead, next one.
Time.
So time, which I'm going to write at the bottom of this list, which I will represent as a lowercase t almost always. There are reasons why we don't use capital T. So when it comes to symbology, capital T stands usually for something called a period, which is reference to things that are cyclic in behavior. So I will tend to stay away from using a capital T. Lowercase t generally stands for either a time period or a specific moment in time. Next.
Displacement.
Displacement, I will have displacement written as a delta x. Delta indicate change in. However, you should become accustomed to writing this as the actual difference of 2 position variables. Displacement is change in position. So technically, this is what you should write. And this is kind of smeared here because, still getting used to the whole writing thing after 4 months of not writing. That's an x with a subscript 0. It's shorthand for writing x at t equals 0 if I was to write it as a function. All right, almost there, 2 more.
Initial velocity.
So, initial velocity, v with a subscript of 0. These subscripts of 0 are called naughts, N-A-U-G-H-T, which I will never spell again. I simply will say x naught and v naught when talking about those 2 variables. And I'm just going to throw out the last one, which you guys would probably say from last year is final velocity. I want to be careful about that. This is velocity at some point in the future. V sub t, or v as a function of t. So generally we will say final velocity in class. That assumes we know that this is in fact the final velocity of the object. Now, these represent the 5 motion variables, but I want to be careful. These really represent what are known as the 5 Galilean motion variables. Galileo is responsible for the mathematics that is associated with uniform accelerated motion. So you guys who are have never heard that phrase before, uniform accelerated motion is the motion that's represented when the acceleration is a constant or is zero. Our class doesn't necessarily assume the acceleration to be constant. That's great for like sophomoric efforts, but we are beyond that. So our accelerations don't have to be zero. We can have non-zero accelerations. Our accelerations don't have to be constant. We can have accelerations that are a function. So to add to our vocabulary just a little bit, since it's kind of fun, there is another variable that's not on this list, which usually doesn't get brought up on tests, but it's fun to know. It's called the jerk. And it's the rate of change of the acceleration. And just the idea that jerk is an actual vocabulary word is kind of nice. Yeah. It really is the definition of the phrase getting jerked around, because it represents a system that's not moving and being forced into motion by a change of acceleration. We tend to be concerned about the jerk because the jerk is what can be significantly harmful to the human body. Having an extreme change in acceleration can be damaging. That's why, we tend to not use springs to launch roller coasters. It tends to kill people because of the extreme change in acceleration. So we use other things for that. Not that there's a whole lot of roller coasters right now. So, let me stop. Let's go one step further with this review. And this is for the benefit of people who did not have physics lab. In a full course of physics, you develop after a couple of moments this idea that you could, through substitution, put together a full range of motion equations. Ones in which they've been solved for almost all possible configurations. These are the 5 Galilean motion equations. They are the least interesting thing in physics. And let me tell you right now, these are not all motion equations. Last year, we weren't particularly specific. This year, we're specific. These are the only 2 that are actually motion equations. And they're only true when the acceleration is a constant. In any other circumstances, these are not motion equations that would fit. They only work when the acceleration is a constant.